All right. How's everyone this afternoon? Okay, so my name is Wei Dai. I'm a research partner at 1KX. We're an early stage focused crypto investment fund. And today I'm here to talk about scalability, in particular about trust minimization and horizontal scalability. So I hope I didn't just lose you guys right there. Raise your hand if you know what trust minimization means. Okay, I see at least 5 hands. Great. What about horizontal scaling? Great, more hands. Okay, so hopefully this is going to be somewhat educational for those of you that raised your hands, and for those of you that didn't, hopefully, hopefully, I will be able to kind of show you something that you didn't know today. Okay, this is the outline. First, I'm actually going to be defining what these terms mean, in particular in the L2 scaling context. And I'm going to be talking about some of the open directions that we have. So first off, what is trust minimization? Largely speaking, there are 2 categories of applications in relation to our blockchain like Ethereum. There are those that are trusted. For example, centralized exchanges, Web2 services, banks, they can connect to Ethereum, but they're always trusted, meaning something can go wrong in the case of, for example, FTX, Celsius, and you will lose your funds. And on the other side, you have trust minimized services. For example, smart contract applications, rollups, as well as validiums. These applications keep your funds safe, even though the operator might be malicious. And so that's what I mean by trust minimization. A trust minimized service, it allows you to have self-custody and allows you to not trust the operator outside of trusting the base layer network. For example, Ethereum. So if we go to more detail, there's actually different properties for L2 that require different levels of trust. And largely speaking, there are 3 of them. Liveness and ordering, meaning you should be able to submit transactions, and they shouldn't, the operator shouldn't be able to censor your transactions. Validity, meaning is your funds being used in a safe manner? Are you getting out the right amount of tokens? And third, data availability, meaning can you actually reconstruct the state of the application and then submit new transactions? And the third one is a really, really important thing that everybody's just trying to solve right now for rollups. And it turns out that every single property requires different levels of trust in different scaling paradigms. And I'm going to stay on the very high level here and just tell you that there's a spectrum here. And on the left-hand side, we have something like Uniswap on ETH1, where you basically are making no external assumptions. And on the right-hand side, you have off-chain services like Coinbase that's completely trusted. But in the middle there, this is where we have rollups, different types of rollups, and also validiums, meaning it's almost like a rollup, but you're not posting data to Ethereum. And OK, let's jump to the second term, scalability. In particular, there's 2 types of scalability. Vertical scalability, we're making a resource bigger. Okay, so 4844 is going in that direction, meaning we're making Ethereum a better DA layer, giving it more throughput. And then there's the other type of scalability, which is horizontal scalability. You are simply adding new instances of a system to make a system more scalable, right? So Web2, it's a clear example of you can add more web servers, you can add more websites, right? But we only have 1 Ethereum. So what about the horizontal scalability of the systems we just mentioned? So if you look at horizontal scalability of these systems in relation to ETH1, you kind of get the following conclusion. On the left-hand side, because smart contracts share the L1 resource, there's always congestion. We don't have any form of horizontal scalability because we run into bottlenecks as we add more smart contracts. On the right-hand side, off-chain services operates off-chain, and they only communicate with Ethereum when they need to, right? When the users enter and deposit and withdraw, in the case of Coinbase. And so you actually have really, really good horizontal scalability. And in the middle is where the interesting thing happen, in my opinion, right? Where we can have trust minimized services, you can have self-custody, but you're able to add more and more systems on top of Ethereum and still not incur any global bottlenecks. And the interesting category here is actually smart contract rollups. So for validiums, these are effectively like they're like rollups, but data is not L1, right? So there's actually no global bottleneck, and for that most people will agree. But for smart contract rollups, I actually want to zoom in a little bit more here. So my argument is that there's going to be two types of rollups, and I'm going to show you which one is which. There's transaction data rollups. So optimistic rollups are mostly transaction data rollups. So whenever you make a request, that entire request goes to L1. And there's state-diff rollups, meaning the part that goes on chain is not your transaction request, but the difference between the L2 system between batches. Okay. So the examples are basic as follows. All the optimistic rollups today that we know of are of the first category, meaning you post the entirety of the data to L1. And in the case of Starknet and zk-sync, they're actually of the second category, meaning the larger the batches it gets, the data that you post to L1 actually gets smaller. And I'll show you some data in the next slides. And this is something that's unique to zk rollups, because you can actually enforce validity even though you're not posting the entirety of data. Okay, so here's some data we collected around the end of 2023. And it's guys over a 30-day period, looking at the average data incurred by a transaction on L1, right? So these are L2 systems. And it turns out after zk-sync made this upgrade around December 2023, they effectively enlarged the batch sizes, and the call data per transaction become a lot lower than all the other solutions. And you can see this on various different charts in the form of transaction cost per transaction, because DA cost is actually the number one contributing factor to L2 fees. So, and actually, if you look closer, for the extremely large batches during those inscription events, the call data per transaction actually got as low as 10 bytes. So basically, what's happening here is for transaction data rollups, effectively you're bounded in the data that you're lower bounded in the data you post to L1 because transactions are of a certain format. And for state-diff rollups, you actually get this aggregation benefits. So as you aggregate more, the less data you need to post to L1 per transaction. Okay, so here's kind of the one of the main points I want to make in my talk today, which is if we want to have Ethereum connected services to scale like Web 2 counterparts, we have to not congest Ethereum L1. Otherwise there's no way to get kind of Web 2 backend scale transaction throughput, right? And really there's two approaches. One, we don't post any data to Ethereum L1, or two, we post really large batches so that you get really a lot of amortization benefits for for the amount of throughput that you have on the L2. Okay, so here's some common questions that I think always get asked whenever I make this argument. And the first one is, why don't we just use an external DA like Celestia, EigenDA, Avail? Well, my answer to this is, first, this is a temporary solution. Ethereum is also working on a better DA solution, right, on ETH1. But this is still a global bottleneck if you use a shared DA layer. We're basically just kicking the can down the road. And we cannot add infinite number of L2s without congesting these data layers if the class of applications gets richer and richer. And furthermore, these external DA services do not inherit L1 security. And the alternative approach is, I think, we should actually create really large batches for these L2 systems and post state diffs to L1. And that's really should be the base case. We can still use external DA services for the full call data, especially if there are actually independent instances for each rollup. And we should always be posting state diffs to L1 to inherit Ethereum security. And the second question I get a lot is, how does all of this relate to shared sequencing, which is also a buzzword these days? And I think the answer is shared sequencing, just like global shared DA, is also a shared resource. And as with all global shared resources, they become bottlenecks as you add more systems. And but nevertheless, I think that's they're a great invention because they allows you to atomically compose between different L2s as if they're L1 smart contracts. So I guess if you haven't seen shard sequencers, I encourage you to look more into Astria espresso systems. Okay, so third question that I get a lot is, yeah, like what about interoperability? You know, as you add these horizontally scalable systems, you're gonna have more and more of them. They're gonna be more and more siloed. Yeah, what do you do about interoperability? So first of all, we definitely do not have atomic composability between these L2s, unless we use shard sequencers, which have global bottlenecks. But I think async composability is also a usable solution, right? We can this can be very, very similar to users as well. So, like, what do I mean by this? There's two great examples of recent kind of paradigms proposed by zk-sync and Polygon. So, if you look at zk-sync hyperchains, it's really a horizontally scalable system where all L2s and L3s, they call it, are connected, right, via a shared settlement. And the same thing applies to Polygon AG layer. And I think this is basically the framework that I think most of these projects are converging on, which is that we should be able to instantiate more systems, and they should actually benefit from being inside the same ecosystem and inherit the same liquidity. Okay. Yeah, so finally, let me discuss some open directions I think are somewhat underexplored currently. The first thing is, of course, what do we do about data availability, right? The entire point of rollups is we should be inheriting almost security. And if we don't want to post as much data to L1 because we have a global bottleneck, yeah, what do we do? What if the data is gone? Well, yeah, so this is definitely a hot topic of debate. And a lot of people in the EF has been kind of there's a resurgence of discussing plasma-based solutions, right? Which is you don't need to put data on one, but you still get the data somehow, and that's basically the entire class of plasma-based solutions. And encourage you to kind of read more on the post from Barry Whitehat and Vitalik linked here. And second, when there's so systems are currently pretty centralized, and there's an argument to be made that they actually give you better throughput, right? Like a single centralized sequencer. But they don't really give you kind of this self-confirmation guarantee in the sense that that transaction it will be confirmed, right? If we're going to make these batches really large, it's going to take a long time before they settle onto R1. How do we get more guarantees for the user that the transaction is going through, right? So ideally, you want a really, really fast confirmation, but settlement could be it takes a lot longer. And yeah, so one example solution is we could, for example, have a dedicated data availability committee. Okay, I should back a little bit. So the problem is the technical solution to this is really called proof of confirmation, where the user, after taking some confirmation from the sequencer, is able to slash the sequencer if the sequencer did not include the user transaction in the place that the sequencer promised they would. So I guess I don't want to get too technical here. So really, there should be a way for the user to prove that the sequencer didn't behave per the commitment. And that mechanism requires data about the system. And that's basically a form of DA problem. And so, yeah, there's kind of this, do you actually have the sequencer share data against other to other nodes so that other nodes can help users fraud proof? In which case, your system is less scalable. Or do you keep the data for the sequencer itself? In which case, the sequencer can just do whatever they want, right? So there's definitely some open questions here. But I think taking the midpoint of doing a data availability committee, this is something that Starcore does. I think it's a good immediate term solution. Okay, and of course, there's a lot of related works. So here's a post on base pair confirmations, which is something that's very adjacent by Justin Drake on ETH Research Forum. Encourage you to take a read. Okay. Lastly, last final direction that I think is really important is we've seen a lot of L2 systems go down, right? Like the centralized sequencer can go down, and they'll just be offline for hours or days, and I think we should be able to recover from these liveness failures much faster, right? If for example, alternative sequencers are always queued up to be able to take over the work if the main sequencer goes down, we'll have much better liveness guarantee. And I think that's like one of the main UX problems of L2s, right? Is that like during periods of high demand, they just centralized signatures just go down. And I think this is definitely a problem to be solved. Okay, so yeah, let me actually skip this technical slide. Not bore with the technical details. So what is the main point? What is the main takeaway? Yeah, the main takeaway is I think to really scale Ethereum connected services to billions and billions of users, to really compete with Web2 scale transaction speeds, right? We really need to have horizontally scalable systems that is trust minimized, that can interoperate, and this is something that rollups by themselves do not really solve, and we should really look into validiums. Okay, and there's a blog post on this that I recently put out, which is called On Trust Minimization and Horizontal Scaling. And if you want to read further, I encourage you to scan this QR code. But otherwise, I think I will end early. And if you have questions, raise a hand. Okay, I don't see questions, and I don't think there's a mic for the audience, so I'm going to be taking questions over there if you do have a question. But yeah, I will stop here. Thank you for your attention.